hull form. Hull form is used for hydrodynamics. So we need to have a strong, because of strength, load coming from the ocean. The biggest one is hydrostatic load coming from weight and buoyancy. Unbalance between weight distribution and buoyancy distribution along the ship surface. And also dynamic ones, such as wave, big wave, a small wave, and motions. But sometimes we can have a too strong structure may cause it to be heavy and expensive. Right? So money and also heavy. So you can think about airplane. The weight is very important in airplane. So the airplane designers are very sensitive to the weight optimization. So comparing to the structure like this one, the building, the weight is not so sensitive to them, to the architecture, building architecture. And ship designer is in the middle. But for the high-speed ships, you may be more sensitive to the weight than slow ship. Right? So overstrong, usually because of the speed and also cost, because of the thickness of the plate, it gives you more money to be used. Function, so strong enough. Mostly, the longitudinal strength is the most important. Longitudinal, because of ship is very slender and long. So longitudinal strength, longitudinal bending. So hull can be seen as a big box girder. Box girder means the box-shaped pipeline consisting of bottom plate, side shell, and then deck. So ship looks like in the middle, looks like this way, right? So it can be seen as a box with a plate. Right. Simply, there are more structures like this one or this one, but simply it can be seen as a box girder. Safety margins. Every designer should have a safety margin. Maximum load throughout the ship's lifetime. So how can you set the design condition? Right? How big is the load on up to this beam? It can be 100 kilogram or 1 ton or 10 kilogram only. You decide. Right? Design load should be. It can be the condition, right? So usually you can do one of them. One is a maximum load through the, say, this ship will be used to transport oil between Korea and Saudi Arabia for 10 years. Then along that 10 years of transportation, what can be the maximum weather condition and load up to this ship? You can calculate from database something along the ship route and seasonal fluctuation. Lifetime 10 years or 20 years, maximum load, then the ship should be stay safe. Or you may use more statistics rather than maximum. So you can say that possibility of breaking this ship for the whole life cycle can be lower than 0.001%, something like this, right? Rather than using maximum, right? Percentage. So that is a more advanced way of doing designing in these days. But still, uncertainty, because we are using statistics, right? storm is coming. So what can be happen? But ships can be escaped from the storm is coming, right? Because there is a forecasting. So anyway, there is a uncertainty. Stochastic should be important. So you need more science and probability and also experience. So we see once again the weight, the balance between buoyancy and weight, right? And buoyancy coming from the pressure. And pressure is increasing according to the depth. And weight is coming from all the load. And but also load is changing along the life cycle and also along the route of the shipping. So lightweight ship, lightweight is almost steady for several months or years, and cargo weight is fluctuating all over the schedule. And every time it should be balanced. Anytime. Right? This is a physics, right? Physics. Buoyancy and force and weight should be balanced at all time, but statically also dynamically. The dynamics gives you somehow equilibrium conditions or equation of equilibrium. Loading condition, distribution of weight and buoyancy over the length. This is very simple one. Sometimes evenly distributed load of cargo, and sometimes uneven distribution of cargo in this way or in this way. And also the wave is coming in this way or in this way. So buoyancy changes, also weight are changes, two changes. So many cases, right? This is simplest, steady. But if weight is only change weight, the wave still stay, but still gives you a bending in this way. We call this a hogging. But if you go in this cargo, then it goes in this way. We say it's a sagging, hogging and sagging. But evenly distributed cargo, but because of the wave, the pressure and buoyancy changes in like this one, so it gives you hogging and sagging. And then complication, right? But only this one gives you a static state. And it is running, wave is coming, wind is blowing, then it goes your dynamics of structure motions. So a complication is coming. Hogging and sagging. So, and if you have a hogging, then the deck side have a tension, bottom side should be compression, and then sagging bending moment because of the wave is in this way. So compression here and tension there. So this can be iterative tension and compression goes many times, right? Wave is coming every time. So it can be fatigue failure is coming also. Right? Fatigue. Size of the vessel. When you enter this room, this building, you may see this ship. This one? Yes. Did you see this ship? Yes. No. Yes. Okay. All right. Everybody sees this. There are another one in the lobby, right? So there are two ships, but this one is vertical. And this ship, if there is a plate here, the name of the ship is Esso Osaka. Osaka means the city name of the Japan, right? And scale model. Scale means this is a rear ship, but this is a scale down ship, but still big, right? Still big. But this is a scale down ship because this one is more than 300 meters. 300 meters. Right, drift and power and speed and displacement. Right. This is for scaled down for experiment. And towing tank is a swimming pool, indoor swimming pool, where this model ship is towed to see how much power we need or force we need to carry this ship at this power of speed and power of resistance, force, power, and in this condition, something like this, right? All different conditions. But anyway, towing tank. There are two big towing tanks in this town, not in this school. We have a very small pool in our university that is only 20 by 20 meter small pool, right, for the test. But for this model ship, there are Samsung Heavy has a 300-meter long indoor pool, and another government research laboratory for shipbuilding, they have a 200-meter long towing tank, right? And that model is for that case of towing tank for the experiment. So size of vessel is very good. You see that scale factor? No, there's no scale factor. Probably that one is 8 meters long or 9 meter long. If we say 10 meter long, then scale can be 34, right? 34 scale. Big scale down. Failure, bending. Bending is the most important for the ship because this is long, slender. But there is also shear like this one, and normal shear and longitudinal shear, and stress and strain. You remember this wording for a long time. Normal stress, normal strain, shear stress and shear strain. But mostly is a bending, right? Bending. Stress and strain. Remember this? Measure of internal resistance in a material, externally applied load, the normal stress, shear stress, and strain is measure of deformation. So normalization is epsilon and psi something. And then normal stress and strain. Normal stress is force or pressure divided by area. So it's a unit area, force per unit area, right? Tensile or compression. And strain is a deflection divided by length. So it's a per unit length. So it is a ratio, right? Ratio. And between stress and strain relationship, we saw there's a Young's modulus, similar to spring, force and spring model, right? K. Or it's Young's modulus. You already see this one a long time ago. Or some, not long time ago, 1 or 2 years ago. Shear stress, right, shear stress, this one, right, shear stress. And stress strains relationship for the shear stress is Fuchs law in shear. And then it comes with a Poisson. Poisson is Young's modulus and what is this? G. Poisson is a lateral strain divided by axial strain. Axial is in this way, a lateral is in this way. So ratio. Okay, and then elastic and plastic deformation. Elastic return back to the same position, right? But plastic does not return back to the original position. Right? Just remember, and then stress strain diagram. So this is the linear or plus elastic deformation region, elastic, linear, but yield strength, and then goes further to ultimate strength, and it goes fracture and necking and strain hardening, Young's modulus, and beam bending. Shipbuilding is beam bending is most important. Beam is this like this is a beam. So ship can be seen as a beam like this one, or box girder shape, and transversal shape is like this one, but long enough, so it's a box-shaped beam. Structure member intended to carry load from the bending. So weight distribution. Columns are primarily to this is a column. This is column. Column is in this compression. Column like this building column. So that is different way to failure mode. And structure comes complexity in this way. This is a rear ship, mid section, rear ship. You can see any person here. Some person here, right? This is looks like a person. Anyway, it's a big structure. Deck beam, shell frame, bulkhead, stiffeners, girders, webs. Right? Bulkhead. Bulkhead is like this one, right? Bulkhead. Deck beam is deck is floor, but beam is something like this one, right? Beam. We already seen this beam. This is a beam, right? And then frame. Frame is like this is frame, right? Frame. So this one is frame. This one frame. Transverse frame, and also longitudinal frame. Longitudinal frame here. There are so many different names. And then girder comes, and then girders. Girders is a little bit bigger size frame, something like that. Bigger frame. So in the middle there is some stronger frame is here. We call this the girder, and then also web. Web is another name of transverse. So we call this a web. Beam loading. We see already this one for many times. Bending moment and shear force diagram, free body diagram. There is a support, simply supported beam, and force is here. Shear force diagram, bending moment diagram. You need to integration and distributed load like this one. Then shear force diagram is complicated, and then the bending moment is further complicated. Integration, right? Integration. And bracket. This looks like a bracket. So when you use a bracket at the end of the beam, then it converts the simply supported beam into a fixed beam, right? And the fixed beam because of this bracket. So that the maximum bending moment at the middle is lower down because of this bracket. Right? Bracket reduce maximum bending moment at the middle to 60%. That's why we are using HEL as a beam. Classical mode of failure, it breaks because of this slender, this break in the middle. Right? Longitudinal strength is the most important in the ship. Hogging and sagging moment in waves. Very simple, but there is a final video. We'll see that hull strength bending moment. I should have, okay, this one is good. Simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it from sources such as the light ship weight, the weight of cargo, balance, fuel, etc. And of course the harsh sea, the wind environment, the movement of the ship, and vibration. The hull may be prepared for simple beam. The force acts on the beam is then deflected in accordance with the magnitude of the force and the strength of the beam. Load generates vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally, and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced from the bow to a head sea. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. All right. Okay, any question? And for